Last time we started section 3.2, we're looking at addition of whole numbers, and we had gotten to the point where we were going to look at some addition algorithms. So there's quite a few algorithms we're going to look at. Each of them sort of have their place. They have things that they're good for, things that they're not as good for, benefits and drawbacks. So the concrete model is really good, and if you think about what we have done and talked about before, it works similarly to the problem that we were looking at the beginning, Ruth, where we were trading things up. Jordan, what's your question? Did we do example 3? We had finished through making 10. That's where we had gotten through last time. Find it? Cool. All right. So the concrete model is actually what we're going to do physically on our screen or on your paper is to draw the images that your students would be doing if they were actually doing tactile learning with the blocks. So you're going to imagine that you have 3 longs. Oh, that's really thick. Let's make it a little thinner. 3 longs, because that's the 30 part of the 34. And you have 4 units. Okay, so that's 34's concrete representation. Then you've got 18, so you've got 1 long, and then you have 8 individual units. Okay, so this is the image of what you're starting with, and you're sort of combining these 2 groups of objects together. And then just like what we were doing, but with other bases in section 3.1, we're going to combine the pieces to make bigger pieces. So for example, these 8 plus 2 more of these would make 10 individual little pieces if you counted them up. And I can sort of trade them in for a long, because a long is 10 of those stuck together. So I trade those up. So I have my original 3. I have the one that was over here, and I have one that I've just acquired by trading up. And then I have the 2 leftover little blocks that I wasn't able to combine together. So this is the result of my exchange. And I can readily see when I collect them all, especially that I have 5 longs, I have 2 units, and so I have 52. Abby, I took your paper off your desk for your homework, because I was grabbing them. So this is concrete model. You can do a concrete model with coins if you wanted to do a concrete model with coins. So if you were working especially at different points when kids are working with money, this is a really good application of that idea. It's a combination of different ideas. But right, if a dime is worth 10 cents and 10 dimes then is equal to $1, and I had 3 $1 bills and I had 4 dimes, and then I had 1 $1 bill and I had 8 dimes, I could put my 10 dimes together and trade it in for a $1 bill, and I could count the same sort of ways. So we can do something like that. So with dollars, or we could do it with $1 bills and $10 bills. There's lots of things that we could do. Blocks is one of them. So this is a concrete model depiction. The one that you know and love is called the standard algorithm. And you know and love it because you've used it for 13, 14, 15 years, I don't know, something like that. You've used it for a very long time. So the standard algorithm, we line them up. We start on the right-hand side, and we say 4 plus 8 is 12, and we write a 2 down below. We write a 1 on the top, and then we add the tens column. 1 plus 3 plus 1 is 5. So we have 52. This model is very efficient. I don't have to use very much space to do it. I can do it pretty quickly, but it's a little bit hidden in what you're doing. This 1 that goes into the next column, what is it doing? Well, it's regrouping. It's one of the reasons why you see that change of language. They don't use the words carrying and borrowing anymore. If you say it, my kids will look at you and go, I don't know what you're talking about. They just will. They use the word regrouping, which is actually a lot better. I know it sounds strange for me to say that, but it is, because what you're actually doing is you're saying I had 12 of these, 2 remain, and 1 is actually 1 10, so I'm grouping it into the tens column. So it's a little bit hidden in what's going on with the way that these pieces are structured. The expanded algorithm is kind of a combination of the concrete model above with the expanded algorithm, with the standard algorithm that we just did. So what the expanded algorithm looks like is writing things down with their place value components. For example, 34 is 30 plus 4, and 18 is 10 plus 8. Now, with this one, it doesn't matter whether you move from left to right or right to left. That's also kind of a nice feature. I can add the 30 and the 10 together first if I wish, which would be 40. And I can add my 4 and my 8 together, and I can get 12, right? And then I can do one of a couple of things. One of the things I can do, if it's straight enough forward that you can see it at this point, you could just add them, sort of straight across, if you will. But you could also break the 12 up into 10 and 2, right? So this is 40 plus 10 plus 2. I'm just breaking my 12 up into 10 plus 2. So 40 plus 10 is 50, and then my 2 makes 52. Now, I've written a lot of pieces down, so this is not very efficient if I write all those steps every single time. But you can imagine how you could abbreviate some of those steps along the way. This is very clear where the numbers are going, what's happening to them as the regrouping is happening. That's a benefit. They're writing all of it down, especially if you were writing all of that down. That's a negative, because there's more writing. The next one is actually called column addition. Column addition actually allows you to work from left to right. So what we're going to do is we're going to write them out, stacked on top of one another. And like I said, we work from left to right. So I've got the 1 and the 3, and the 1 plus 3 is a 4. And it's a 4 in the thousands column, so it's 4,000. So what I've literally done is I have added 1,000 plus 3,000 on the first line. And then I go to the hundreds place and I do the same thing. I've got a 5 and a 2, so that's 7, and it's in the hundreds. What I've really done is the 200 plus the 500. Now, the work that I'm putting in parentheses out to the side, you don't have to show that. I'm writing it for your benefit so that when you look back at this later, you're like, where'd all those zeros come from? You remember. Okay, that's not really part of the algorithm, but that's what's underpinning this. I have the 3 and the 1, so that's 40, because I'm really taking 30 plus 10. And then I have my 4 and my 8, which is 12. And that's the only one that I've actually added as they are because it's in the units place. And then because they're still all in columns, nice and neat, we can add from left to right or right to left at this point. So I've got a 2 here, a 5 here, a 7 here, and a 4 here. This is nice because it keeps each of the place values separate. It's nice because it allows me to move from left to right, which is how we read. You probably don't even think about the fact that you do your math from right to left at a very young age when you do all your reading from left to right. That's a little confusing. So this allows us to go from left to right. Again, there's more writing. Now, the reality is that none of this over here would be written, right? We would just be writing the column stuff down if we were doing the algorithm. But it is more writing. Our next one is called the Lattice Algorithm. And this is a very interesting one. It has a really nice visual to it. So we're going to write the same thing we did before, how I'm writing my values stacked on top of each other. I'm spreading them out just a little bit, and you'll see why below. So below them, you're going to draw a box, like a long rectangle box. Really only needs to be as long as the numbers are. Let's try that again. There we go. And I'm going to split each box so that it has a place value underneath it. This is not great. Let me use a freehand here. Okay, so there's a box underneath each column. And then we're going to split the boxes in half, but we're going to do them at a diagonal like this. So this is why it's called a lattice, is because of this image. Again, you can move from left to right or right to left. Doesn't make any difference. I'll move from left to right just because I can. And we're going to add columns. So 1 plus 3 is 4. And we're going to write the 4 in the bottom corner of the lattice. So same column, but it's down here. 8 plus 2 is 10. So when I write the number 10, the 1 goes in the top corner and the 0 goes in the bottom corner. 9 plus 1 is another 10. And then 4 plus 8 is 12. So I do the 1 on the top and the 2 in the bottom corner. So again, I can move from left to right. I can do all the individual place values one at a time. That's all really nice. But what I do to get my final answer then is I add along the diagonals. So here's my diagonals. Not drawn very well, but imagine. I do have to do this step from right to left. So in this first diagonal, I have the number 2, like this. My next diagonal takes the tens place from this 12 and the ones place from the tens column because they're both in the same place value now, and I add them together. And I do the same thing along my next diagonal, 1 plus 0, and my last diagonal, 4 plus 1, which is 5. So my solution at the bottom is the 5, 1, 1, 2. So it's isolating the individual operation steps, but then it does all the regrouping in a very visual way. This is lattice. The very last one that we're going to look at is called the opposite change algorithm. So what the opposite change algorithm's goal is to turn one of these numbers into something with lots of zeros. Right? So, for example, the number 488 is really close to 500, right? Or you could say the number 231 is pretty close to 200. I don't care which one you necessarily use, but your goal is to take one or the other one of them and to turn it into that nice value that's very close or close-ish, and it's got lots of zeros in it. We're going to do it with our 488. Okay, so we do it place values at a time. So we've got 488 plus 231. And again, I'm going to write it horizontally because that's how addition is typically done with kids at this age, is this horizontal or this vertical description like this. So what I'm going to do is I'm going to add the number 2 to the top value. And why am I going to do that? Well, because it takes the 8 at the end and it gives it a 0 value now. 488 plus 2 is 490. But opposite change algorithm means that if I added 2, I also need to subtract 2 as a balancing step. So I will subtract 2 from the lower value. So that gives me 229. Okay? Now I think about the tens place, because I've been working with the 488, now I'm working with 490. What do I have to add to 490 to turn it into that 500 that I'm wanting? 10. So I add 10 to this one, which means I subtract 10 here. So this one becomes the 500 I'm looking for, and this one would become 219. Once I have a single value followed by the zeros, so the 500, the 1,000, the 400, the 490, I'm still not saying it, the 4,000 instead of like 3,999 or something, right? Once we get the single numerical value followed by a whole bunch of zeros, then we just add the way we would before. 500 plus 219 would be 719. Now, perhaps not with the number 488 and 231, but I do this when I add things together in my head a lot with mental stuff. I take something away from this and add it to this one so that I get nicer values to keep in mind and keep to work with. So this is an algorithm that, like when I'm shopping and I'm trying to estimate what's in my grocery cart, I actually do this kind of frequently. So this is the opposite change algorithm. And I totally lied to you. I said there was only one more, and I have one more after that one. I'm sorry. Scratch algorithm. Okay, this is the last algorithm. This algorithm is really, really good when I have a list of numbers. Scratch algorithm is practically pointless if I only give you 2 numbers. So that's why you see there being a list of numbers as I'm giving you this example. The other ones that we were doing before are better when we're working with a single, like two values that I'm adding together, not a whole bunch of numbers. So here's the way the scratch algorithm works. We're going to line them up vertically again, right? 34, 18, 69, and 87. So this is a little bit like the standard algorithm. We are going to work from right to left. The tricky thing that happens when we're adding up lists of numbers is that there comes a point when we are adding that we're no longer using addition tables that are memorized values. So let me show you what I mean if we were to do this in the traditional algorithm. 4 plus 8 is 12. Now I have 12 plus 9. That's 21. But nobody ever memorized an addition table that said 21 plus 7. I know it's 28. I understand that. But do you understand what I'm saying? Like, that's not in a standard traditional, like, and in 21, what was it, 21 plus 7? 21 plus 7 is really nice, but what if it had been 25 plus 7 or 28 plus 7? It becomes more difficult depending on the numbers you're working with. So what Scratch algorithm does is it allows us to stay in our single addition facts addition tables. So here's how it works. You have 4 plus 8, and that equals 12. As soon as you get a 2-digit number, you scratch. I'll do it in a different color just so that you're drawn to it. I didn't scratch the right one. Sorry, that one. You scratch where you got your 12. And instead of remembering 12, I only remember 2. And now I'm going to do 2 plus 9. What is 2 plus 9? It's 11. That's a 2-digit number, so I'm going to scratch. And I'm not going to remember the number 11 anymore. I'm going to remember the number 1, the ones place. And then 1 plus 7 is 8. So what did I actually do? Well, I scratched every time that I would have had to carry or regroup a tens value. So every one of my scratch represented a tens value that I ignored along the way. I ignored the tens value here when I got 12. I ignored the tens value here when I got 11. So I ignored 2 tens values, so I'm going to carry 2 tens to the other column. That's my 2 scratches. Then I go from 2 plus 3 is 5 plus 1, 6 plus 6, 12, so I scratch. And I remember that I have a 2. 2 plus 8 is 10. I am going to scratch again, although it feels a little bit funny because, when I have 10 and I forget the tens place, I just have a 0 now, right? But that 0 is what I write down here. How many scratches? 2. 2 scratches moves over into the hundreds column. There's nothing else there. So I add that 2 to nothing else, and I just get 2. So it's 208. It keeps my addition facts smaller. That's what it does. It keeps them smaller so that I don't have to remember as much as I'm adding down my column. Okay, so what we're going to do next is we're going to take a look at addition with those other bases that you know and love so much and how they work in those bases. And what I'm going to show you on each of them is how they work in a couple of the different algorithms. Okay, so there's nothing special about the algorithms I'm necessarily going to pick. I'm just going to choose one, and we're going to take a look at what it would look like in that algorithm if we were to do it with a specific base. So the first one that we're looking at is actually a base 8 number. So we are going to add 3 4 base 8 and 1 7 base 8. And the first thing I'm going to do is going to use the addition, the standard algorithm that we've learned for addition. So you can think through it from the way you're most comfortable with adding in an uncomfortable base. 4 plus 7 is 11. But I'm in base 8. So what I have to think is, I have the number 11. How many 8s is that? 1 8, which carries over. And how many left over? 3. There's 3 leftovers on bottom, and I carry or I regroup the 1 8. That's what you guys do every time you do carrying or regrouping with addition in base 10. You carry over the 10s. How many 10s do I have? How many 1s are left over? And then in this column, I have 1 3 and 1, which gives me 5. So this is 5 3 base 8. Okay. I wrote down scratch addition here. I'm not sure I really want to do scratch because it doesn't work all that great. We'll do column addition. That'll be okay. I'm just going to do lattice on the next one, so we'll do column addition. So this is the standard algorithm first. It's often your choice which one you do. You don't have to do things twice. I'm just showing you a couple examples. Yep, Hallie.
Can I ask a question about the standard?
Sure.
So if the tens place were to add up to something bigger than 8, would you do that again?
Yes, you would.
And then carry it?
Yeah, like let's say this added up to 9.
Okay.
You'd regroup one of them to be in the next 8's column over, and you'd write the one left over underneath.
Okay.
Yep, you're right. Okay, so let's do column addition. So I have 3, 4, and I have 1, 7. Column addition, if you'll remember, lets us move from left to right. So the 3 and the 1 give me 4 8s. And then my 4 and my 7 give me 11, like we did before, but that's 1 8 and 3 left over. And then I can add them from here. Okay, so this one, just as a reminder, is the 3 0 plus the 1 0. And this one is the 4 plus the 7, which is 11, which is 1 8 and 3 left over. That's where that's coming from. Okay, we're going to do one more with a different base. We're going to do base 3. So remember in this one, I'm grouping things in 3s. Okay, I don't have any 3s, I have 0, 1, and 2. So we'll do our standard algorithm first. So I have 1, 2, 1, 2, and I have 1, 1, 2. So the standard algorithm, I start on the right-hand side. I have 2 plus 2 is 4. How many 3s is that? 1 3. So I'll regroup the 1 3. And how many left over? 1 left over. The 3s column, I have 1 plus 1 plus 1. That is 3. How many 3s is that? 1 3. And how many left over? 0. Now I've got my 3 squared column. 1 plus 2 plus 1 is 4, which is 1 3, 1 left over. And then in my 3 cubed column, I have 2. So this is 2 1 0 1, base 3. Make sure you're writing your subscripts for your bases when you encounter them. I'm going to do lattice was the other one I was going to do on this one. So we have, I need a little more space than that. 1 2 1 2 1 1 2. And I have my columns. And then split along the diagonals. Left to right, right to left, doesn't matter. Here's the 1. 2 plus 1 is 3. Yeah? So I'm right here. And this one, 2 plus 1 is 3, which is 1 3, 0 left over. 1 plus 1 is 2, so that goes in the bottom corner. 2 plus 2 is 4, which is 1 3, 1 left over, like that. And then if you'll remember, we add along diagonals. So I have to start on the far right for this to work. My far right's a 1. But then on this column, we didn't see this happen before. It can happen in base, any base too. We just didn't see it happen before on ours. I have 1 plus 2, which is 3, right? But that's too big because I don't have a 3 in base 3. So I will carry that 1 over. Let me use red to show I'm carrying it over. And then I have the 0 down here. Now I have this 1 and this 0 for a 1. 1 and 1 is 2. 2 1 0 1. Base 3, just like before. Okay, any questions on those? You're not going to do a whole ton of them. You're just going to have a few. Grace.
When we're writing subscripts, do we have to write out the word, or do we?
It's a really good question. So your book uses the words. I would prefer you to use the words. There are other books that will do something like this, where they put the subscript in parentheses. If you choose to do that, just be super, super careful that this really looks like a subscript and not like you're multiplying something by 3.
Oh.
That's kind of the problem, is that notationally speaking, it can be confused. So, all right, I want to look at a few strategies for mental math. So we talked about something where we were adding from left to right before, and this is another location where we see that idea happening. So mental math from adding from left to right. So if we were adding 46 plus 38, one way to do that is to add the 40 and the 30 together first. So 40 plus 30 is 70. And then I can actually add my 6 and my 8 together to give me 14, and there's my 84. We mentioned, I can't remember when it was, the last couple of class periods anyway, somewhere, that the idea of mental math, actually it may have been my other class, so I apologize if that's true. The idea of doing mental math means that you have to show me what you're doing, but it needs to be something that could have been done in your head without the showing me part. And basically anything that requires more than about 3 steps is not considered mental math because you're having to hold too much information simultaneously in your head. So 3 steps is sort of about it. This one was 3 steps. I added 2 different pieces together, and then I added them together a third time. So 3 steps is about the capacity that we're looking for here. So this is one way of doing mental math, where we're adding from left to right. Another one is breaking up and bridging. I really like this one. What breaking up and bridging does is it takes the second, I say the second number, it doesn't really have to be the second number. It takes one of the numbers and breaks it up. We'll do the second number, 30 and 8. And what it does is it adds the first number, namely the 46, to the broken up first piece, the tens place piece, 30. Well, 46 plus 30 is 76. And then you add on the ones place. And 76 plus 8 would be 84. So you're sort of breaking it up and adding it in separate steps. So this actually ends up being a 2-step addition problem. You could possibly say that breaking it up is the 3rd step if you wish, right? 38 breaking into 30 and the 8 is. Maybe a little bit questionable on that, but even so, you're still within your 3 steps. Trading off, which is what we actually called before, opposite change. Is another mental strategy. So what we're doing when we're trading off is we're taking one of the numbers and we're trying to make them into a nice value of zeros. Lots of zeros is what we want, right? As many as we can have after the first digit. So the easier of these 2 numbers to get to be 0 at the end of it is going to be 38, right? So we take our 38. I'll write them beside each other like this, since we were doing this before, 46. And we add to the 38, which means that we have to subtract from the 46. So 46 minus 2 would be 44. 38 plus 2 would be 40. And then the addition, component-wise, is quite simple because there's lots of zeros involved. Again, 3 steps. Took away 2 from one and added it, added 2 to the other to add it, and I added the results together. So this is one that I will use frequently when I'm estimating, and I'm using it for estimation purposes, not for exact purposes, but estimated purposes when I'm shopping. This is another one when I'll use for shopping a lot. It's called compatible numbers, and I've mentioned this before. It's not exactly the same thing as, but it's kind of like making 10. So if you remember, we talked about making 10 in an earlier lesson, the earlier part of this lesson, in fact. And what we said is sometimes it's really nice to group certain things together because they add up to 10. Well, we can do that with any values. It doesn't have to be 10, but 100 works as well. So for instance, this list of numbers is very nice because look, 30 and 70 is very nice. 30 and 70 is 100. Do you see any other very nice pairs? Yeah, 40 and 60 is another really nice pair to give me 100. So now I have 100, 150. My total is 250. And while you might look at those and say those wouldn't have been that hard to add to begin with, it still would have taken you a fair bit longer than what it just took us right there by noticing that there's some really nice relationships among the values we were given. So these are using compatible numbers. And then again, kind of like the making 10 strategy, this one is going to be, we're going to make compatible numbers. So we're not using them because they aren't compatible. There's only 2 numbers here anyway. But we're going to make them compatible by taking one of them and breaking it into something that actually matches up nicer. For example, 68 would be much nicer if it were 65 and 3. Why is 65 and 3 better? Do you see? 65 and 35 is 100. And then I've got my extra 3 that are left over. So this is, these 2 added together is 100 plus my 3, so this is 103. Okay, so there's 2 things that are happening at the end here. We finished a section called mental math, right? Where we're finding the exact value by doing some restructuring, reorganizing things. The next section, which often gets confused with this, is estimation. Estimation means we're not going to get the exact answer. It's going to be something close. So estimation, the first one we're going to look at is front-end estimation with adjustment. So front-end estimation means that we take the first values and zero everything else out and add them up. So I really take 300, 400, 200. This is the front end part. I'll abbreviate it FE. So 300, 400, and 200 would be 900. Is that good? Okay, this part where it says the with adjustment means that I'm taking the leftover pieces and I'm trying to get them sort of close to things that seem compatible. So if you look at those list of 3 numbers, do you see any 2 of them that you could put together and say, that's approximately equal to something else? What are they approximately equal to? 90, or even if you said 100, it would be okay. You're close, right? So 100 is more friendly to work with. I don't think that's how you're supposed to say that. But it's friendlier to work with. So we're going to estimate it to being about 100. And then at this point, I have the 900, the 100, and the 25 here at the end, just the 25 part. And if I added those 3 together, I would have 1,025. And of course, it is an approximation that I just found. Okay, so the adjustment part is grouping things together and saying it's about equal to, from that perspective. Another estimation strategy is to group things with nice numbers. Well, we called this compatible numbers up here, right? Well, our numbers are not going to be exactly compatible. They're going to be close to compatible. We're looking for close to compatible pairs. So do you see any 2 things that you might say, I could probably put those together, and they're about equal to 100? And there's more than one way to do this one, because I've had people do it different ways. Okay, 35 and 64 sounds great. Those are approximately equal to 100, right? Yeah. Any others? Yeah, the 55 and the 42. They're approximately equal to 100. And you might just go with the 71 and say we're at about 70, right? You're going to just round it down a little bit or round it up a little bit. And so we end up with a grand total of about 270. And just to let you know, in my notes, that's not the approximation that I have. The approximation I have in my notes is actually 255. But we're approximating because I grouped my numbers differently. Jordan.
So will these type of questions mirror homework?
Yes.
And so will we need to get, is there like a range that you're looking for? Or
I'll be looking at your work, or the grader will be looking at your work to see that you've grouped things together in reasonable ways. It's all about the work driven. Yeah. Yeah, so we are at the end of class. We will finish this one next time and do the group work for this next time. I realize we're pushing a little bit behind. It's totally fine. We'll get caught up at some point in chapter 3. I just can't remember which section it is that's a little bit shorter. So we will finish this one up next time, and we will move on next time as well into 3.3. So have a lovely rest of your day.